Hello and good evening, everyone. My name is Jamil Siddiqui, and I'll be here tonight to help you out with taking some derivatives in calculus. So if you can hear me all right, if you wouldn't mind over in the chat section, just giving me a thumbs up or a hello or a good evening, I'll know that you're out there listening, and we'll get started. Tonight, we're looking at an introduction to finding derivatives. And what this assumes is that you've already gone through the limit definition of the derivative, and now you're starting to think about some of the shortcuts that are necessary to help you take these derivatives. So first thing I want to do is remind everyone to follow us at Think Fiveable. You can follow along and get updates on all the things that we're covering and everything that we're going to be streaming throughout the course of the week in the upcoming school year. In this stream, what we're going to be looking at, first thing you got to do is there are certain derivatives that you just need to know. I refer to these derivatives as the one-step derivatives. So you're going to hear me using that phrase a lot. We're going to get into some details to what they are. Again, I refer to them as the one-step derivatives because basically these are derivatives you can take in one step. You just look at them and you will know those answers. So we're going to be talking about the one-step derivatives. Over the course of the year, there are going to be about 13 one-step derivatives you'll cover in AP Calculus. I'm going to focus on 7 tonight, and we're going to start with those. But if you have other questions, please feel free to put them over in the chat, and I'll answer them as they come up. The next thing we're going to do is we're going to talk about some of the rules associated with differentiation. Now, for those of you who have gotten a little further, you may have heard of a product rule or a quotient rule or a chain rule. We're not quite going to get that far this evening. We're really just going to start off with the basic derivative rules. If you want some help with the product, the quotient, and the chain, that will be coming in future streams. But tonight, we're just going to start with the one steps and see how those are used. So without any further ado, let's take a look at what I refer to as the one-step derivatives. Again, we're going to be covering what I refer to as the first 7. The first one-step derivative that you need to know is the derivative of x to the n. And quite simply, that's just the variable x, the single variable x, raised to any power that is a number. It has to be a constant. We use n because it stands for number. So as long as you get your independent variable, which in most cases will be x, raised to a number, that is what this one step is all about. So the derivative of x raised to a number is going to be the number times x raised to the same number minus 1. So you may be familiar with this rule. You might have seen it already. So just as an example, x to the 10th, for instance. If you were taking the derivative of x to the 10th, that answer would be 10x to the 9th. So that's the first one step we're going to be talking about. I always call it x to the n. We're going to do 6 more tonight, and those 6 are your trigonometric functions. So every basic trigonometric function also should be considered to be a one-step derivative. I've got those 6 derivatives written out for you on this screen. We've got the derivative of sine x is equal to cosine x. The derivative of cosine x is negative sine x. The derivative of tangent is secant squared x. The derivative of secant x is secant x tangent x. The derivative of cosecant x is negative cosecant x cotangent x. And the derivative of cotangent x is negative cosecant squared x. Now, if you're new to calculus and you're just starting to learn these derivatives right now, you might be wondering, is there a good way to remember these? So I've come up with a couple of different things I want to show you that can help you to remember these derivatives. So in order for me to share that with you, I'm going to need to switch to my other screen. So if you'll just give me a moment, we're going to jump over to my tablet. And again, the idea here is there a way that we can remember these 7 derivatives fairly easily? So the first one is x to the n. And again, I want to point out a couple of things that I can write on the tablet. The first thing I want to point out is this x right here represents the independent variable. And it's imperative that these 2 things match. As long as those 2 match, it doesn't matter what the symbol is. They could both be t's, they could both be thetas, they could both be w's. It doesn't make any difference what the symbol is. What matters is those 2 things match, because you need to have your independent variable matching the base of that function. So now that I've made that clear, the derivative for x to the n, most people remember this one pretty well. Bring the power down and then subtract 1 from that power. So it's nx to the n minus 1. Again, I find that my students have a very easy time remembering that just by doing some examples. It kind of sticks with them. It's a nice pattern to have. Now it's the next 6 that I really want to focus on so that you guys can really have a good way to remember each and every one of these derivatives. So what's nice about this is the derivative of sine. When you think trigonometry, the 2 functions I always think of are sine and cosine. So it's pretty nice that the derivative of sine actually ends up being cosine. And most people, again, will remember that one. Okay. So now, in order to get you to remember the remaining 5, what I want to do is just share a couple of stories that I tell my students to help them remember. And the first story I tell them is about a deal I made with my mom when I was a student. My mom was very, very, very good about making sure that I did well in school. She had one rule, just do your best, and if you get A's and B's in all of your courses, you're never really going to have to worry about me being angry. So because of that, I always got a little worried that anytime I thought I might be getting close to a C, that would not be a pleasant experience for me, because mom wouldn't really be very happy with me. So I started connecting the idea of C's being negative. And little did I know all those years ago that when I became a calculus teacher, that would actually become very useful, because when you're talking about the one-step derivatives, any function that begins with C has a negative derivative. So right away, I'm going to go and I'm going to put in negatives for the derivative of cosine, cosecant, and cotangent. All 3 of those answers are going to have negative derivatives. So now, building off what we said before, the derivative of sine is cosine. It's kind of nice that derivative of cosine has a factor of sine in it. It's just that has to be negative. So it's almost like a kind of a reciprocal agreement here, that since the derivative of sine is cosine, the derivative of cosine will be sine, but you got to remember the negative. If it begins with C, the derivative is going to be negative. So now we get to the next one, and the derivative tangent is kind of like the way I teach is, if you can remember the derivative tangent, it's almost like buy that one and get the other 3 for free. So what I want to do is I want to show you a little visual that helps me to remember the derivative tangent. So this goes back to one of my teachers in middle school. He always liked using those worksheets that were attached to the teacher's manual. Well, we ended up doing all sorts of worksheets that year, but the ones that I always thought were the easiest were the fill-in-the-blank worksheets. And it was even easier when they gave you a word bank. So what I've done here is I've given you the space to fill in 1, 2, 3 blanks. Okay, so we're going to fill in these 3 blanks, but I've given you the word bank down below. So we've got to use these 3 words to fill in those 3 blanks. Now, if you remember, we left off with the derivative tangent. So if I want to find the derivative tangent playing this silly game, tangent goes in that blank, and then the only words left are secant and secant, and they have to go there, which actually works out great, because the derivative tangent ends up being exactly secant squared. So the idea here is that you've got 1 tangent and you've got 2 secants. So if we go back to the previous screen, we can now put in the derivative tangent is secant squared. But what's nice is this idea now translates to the other derivatives as well. So let's go back to our fill-in-the-blank page, and let's reset everything. So we've got our words back below. Well, this time, I know the derivative tangent is secant squared, but now I'm looking for the derivative secant. So if we play the same idea and we put secant in this first blank, the only 2 words left are the secant and the tangent. And what we find out is the derivative of secant is exactly secant tangent. So this idea of remembering 1 tangent to 2 secants becomes extremely important when you're working with trigonometric derivatives. So going back to the last page and filling that one in, we now know that the derivative of tangent, I forgot that, the derivative of tangent is secant squared. And the derivative of secant now is secant x, tangent x. So for both of these, that relationship of 1 tangent to 2 secants is coming through. Now you may be wondering, well, how does this relate to cosecant? Well, if we come back to this screen and we think about this as an equation, okay? So the thing about math that I find so powerful when you're the one who's doing the math is you're really in charge of the problem. I have a saying in my class, I'm not afraid of the equation should be more afraid of me. I'm the one that has all the power in the relationship. And the reason for that is because we're allowed to do anything we want to an equation, as long as we do what? Okay? As long as we make sure that's balanced, as long as we make sure that we do the same exact thing to both sides. So here I am, I'm looking for the derivative of cosecant now, but I've got the derivative of secant. So what I do is I tell my students, okay, I'm going to do the exact same thing to both sides. And the thing I'm going to do is not very mathematical, but it helps my students to remember their derivatives. I am now going to write co in front of everything on both sides. So if I do that, I've got the derivative of cosecant being cosecant cotangent, but there's just one little problem with that. You got to remember, since it begins with C, that answer actually has to be negative. So this problem ends up being the derivative of cosecant, and we'll go back and write over here. The derivative of cosecant is, the negatives are already there, so it's cosecant x cotangent x. So again, the idea is that if you've got one tangent, it's attached to two secants, whether it be a tangent or a cotangent, it's still one tangent to two secants. So if you're following this along, the last derivative should almost solve itself because we've got a tangent, or in this case, a cotangent, and we need to fill those other two blanks. But every one tangent goes with two secants, but since it's a co, they've all got to be co's. So if we come back over here and just reset the word bank, what we're going to find out is that when we reset all these, we take these back down, we clear them, and we come over here. And now the question is, oops, how do I do the derivative of cosecant? Well, again, if we know the derivative of secant, I'm sorry, how do we do the derivative of cotangent? If we know the derivative of tangent is secant times secant, then to change these to cotangents, we just have to go and write co in front of everything. So now the derivative of cotangent is cosecant times cosecant, but again, because it begins with C, you've got that negative already there, so the derivative of cotangent is cosecant, a negative cosecant squared x. So if you think about these 7 derivatives and you just keep these kind of ideas in the back of your head, it's almost a nice way for you to try to remember them. Okay, so the idea now is that we want to see how to use these one-step derivatives when we're actually taking derivatives of different functions. So we're going to jump back over to the PowerPoint slides, and we're going to look at a couple more rules. So here we go. Okay, so here are our one-step derivatives. From here, what I want to do is bring out a couple of basic differentiation rules. And there are 3 that I want to point out to you tonight. But before I get into these differentiation rules, I just want to back up one step. I want to make sure that you understand you can only use the one-step derivatives if your function looks exactly like these 7 problems. Even the slightest difference is gonna cause a hiccup on your derivative. So you've really got to stress the idea that it's got to look exactly like these 7 problems. So a few more general differentiation rules you need to know. The first one, if you're taking the derivative of one function plus another, and I like to say if you're taking derivative terms, it follows this common sense idea that it's the derivative of the first term plus the derivative of the second term. So the idea is that you can go separately. You can take the derivative of the first piece, and then you have to take the derivative of the second piece, and you can combine them by either using addition or subtraction, whatever is appropriate for that problem. When you take the derivative of that first piece, the derivative of f of x is going to be written as f prime of x, and the derivative of the second piece will be g prime of x. So again, there's a lot of notation here, but the bottom line is you just have to remember this. You can go term by term when you're taking derivatives. That's the idea. Every term can be done individually. The next derivative rule you want to understand is the derivative of a constant. Now, I want you to notice that the letter we're taking the derivative of in the brackets is c, and the letter on the bottom of our d over dx is x. That's important. The denominator of our derivative, where we have dx written there, that is telling us the independent variable. If you look up at the top rule, you've got a dx in the denominator, but you've got f of x and g of x as your functions. This works out perfectly because the independent variable matches. The independent variable of f of x and g of x is x. The independent variable on the bottom of that derivative operator is dx, or just x. So you're taking the derivative with respect to x of a function as using x as an independent variable. When you get to this next expression, I've got d of c over dx. Well, c doesn't match the x. C is not an independent variable. And in most math classes, we like to use the letter c to represent a constant. So now what we're really asking is, what's the derivative of a constant? Well, I'm going to ask a question from you guys, and I want you to put it over in the chat just to make sure you guys are still with me. When you say derivative, what do we mean by a derivative? In one word, what is derivative? What does it mean? So give me some ideas on what you've got there. And Christiana, there you go, right away. Slope. That's exactly it. Okay. Jack, thank you. Sierra, great. So now we've got that the derivative really means slope. So when you look at C and you think about that function C, what does the graph of a constant look like? Okay. So again, give me an answer over in that chat. When you're talking about graphing a constant function, and Christiana, thank you very much. It's a horizontal line. So when you're talking about the derivative of a constant, what you're really saying is, what is the slope of a horizontal line? Well, let's see it over there again in the chat. You get a horizontal line. What is the slope of that horizontal line going to be? And here we go. Emmeline and Ryan, you guys have got it. We're talking about having a slope of 0. So the derivative of any constant is just going to equal 0. And that is an extremely useful thing to know. So if you're ever asked, what's the derivative of 5? The answer is 0. What's the derivative of 21? The answer is 0. What's the derivative of negative 2/3? The answer is still 0. All of these constants will be graphed as a horizontal line. They're all going to have a slope of 0. So that's a nice way for you to kind of remind yourself why the derivative of a constant is 0. And then the last differentiation rule we're going to look at, and again, we call that one the derivative of a constant term. But the last one we're going to look at is when you have the derivative of k times f of x. Now, again, independent variable in this problem is x. We're taking the derivative of a function, f of x, which has an independent variable of x, so everything matches perfectly there. But we've got this k written out in front of it. So that k is attached by multiplication. And because k is not an x, k is not playing the role of a variable, k is playing the role of a constant. And again, we typically like to use c or k for our constants in calculus. So we're asking what happens when you're taking the derivative of a constant times a function. And I refer to this as a constant factor. Well, the rule for this, which can be proven going back to the limit definition, and if you were watching our last stream just an hour ago, that's what that stream was all about, the limit definition. If you go and you set this up, you're going to find out that that constant just gets carried along step by step by step the entire way through. So what this really does is it says, bring your constant out in the front, take the derivative of that function by itself, and then once you've got the answer to that derivative, now multiply that times the k. So when you take the derivative of this f of x, you're going to get f prime of x, and then k times that f prime of x will be your final answer. I personally like to call this the free ride rule, because to me, I'm giving that constant a free ride. But if you're really being more descriptive about it, what we're saying is it's the derivative when you have a constant factor. That constant factor gets a ride to the answer, and then you just take the derivative of the function that's left. These are the three derivative rules that are general rules that apply at all times in derivatives. So again, term by term, you can take terms, derivatives separately. A constant term, a constant by itself, that derivative is always going to be 0. And a constant factor, if you see something being multiplied by a constant, give that constant a free ride to the answer and take the derivative of the piece that's left. So keeping these in mind, along with the one steps, we are now going to look at a bunch of examples this evening, trying to get you guys really comfortable with taking derivatives. So I'm going to switch back over to the tablet. And here we go. And we're going to take a look at some of these examples. So here's your first example. And one thing we want to do as we go through these examples is not only concentrate on the derivatives, but also concentrate on making sure that we're using the correct notation. Okay, so what you're going to notice in this one right away is I've kind of switched the notation from function notation to a y equals notation. Not a big deal. You know, f of x and y are the same thing, so this really shouldn't matter. But if you've done derivatives in your class already, you may have noticed that there's really 3 different ways to write the derivative. Let me kind of quiz you guys a little bit, give me some feedback. What are different ways you can actually write the symbol for derivative? Please put that over in the chat. All right, perfect. First 3. You guys nailed it. Y prime, f prime of x, and dy over dx. These are the 3 different ways that you can write the derivative. So all of them mean the exact same thing, but I just want to take a moment to talk about this notation because it's the first example we're doing together. So I want to point out some properties of this notation. The first thing I want to point out is that whatever variable that you're using in the numerator, that is always going to be the dependent variable. All right. We're going to be talking about functions the majority of the time, not every time, but the majority of the time. And the dependent variable is the output, and the independent variable is going to be the input. And we're so used to seeing y all the time that we just assume it's going to be the dependent variable, and we assume x is going to be the independent variable. But you really got to use your notation. And luckily for us, the derivative is going to solve that for us. Again, the top is going to be the dependent variable, and the bottom is going to be the independent variable. So there should never be any confusion about which is which. This is the reason that the dy over dx notation is really kind of nice, because it gives you this information right away. If we think about the other notations, if we think about f prime of x, all right, well, again, we've got this idea of the independent variable being displayed on the inside of the parentheses. So we know that's going to be the independent variable. And now f and y are kind of interchangeable. We use f of x and y to mean the same thing. So f is really playing the role of the dependent variable in this case. So you get the same information, but in a different form. The third notation, which I tend to use the least, is y prime. It should make sense that, if f prime of x is going to be one of our notations, then y prime would be the same. F of x and y are generally considered the exact same thing. The problem with y prime, in my opinion, is you lose that information about who the independent variable is. And remember, when you're talking about one steps, it's incredibly important to keep track of the independent variable. So that's kind of a rundown of the three different notations and how they're used. Let's take these ideas and let's go take a look at this derivative and see if we can take it correctly. So in my class, the first thing I ask my students is, when you're asked to take a derivative, yes, is it a one step? Is it a one step right away? So I think everyone will look at this and say, well, hey, I've got x to the fifth. That is exactly x to the n. There is no question that is x to the n. It looks exactly like it. Now, when you go to negative 6x to the fourth, we can have some discussion about this, because the x to the fourth is exactly a one step, but the one step doesn't have a negative 6 hanging off of it. So is this still something we can do just by looking at it? Well, this is where your other derivative rules come into play. We've got the constant factor, the free ride rule, that says if you have a constant factor, just put it in the answer. So when it comes time to take this derivative, that negative 6 is not going to play a big role, and we're still going to be taking the derivative just x to the fourth. So as you're going to watch, we're going to handle this as a one step. Just got that one extra piece of making sure we give a free ride. And when you move to the next one, this 1/2 x squared, it doesn't matter what the constant is. 1/2 is a constant all the same. So this is going to work the exact same way as the previous problem. And then we get to this last one. Hey, that's our constant term. And we know the derivative of constant term every single time is going to be 0. So we do have the ability to take these going term by term. So here we go. I'm going to start off with the x to the fifth. And I am just going to use the x to the n derivative for that. So if you remember that, that's nx to the n minus 1. So this guy, when I take its derivative, is going to become 5x to the fourth. Now when I go to do the next piece, to me it's imperative I give that negative 6 a free ride to begin with, okay? And I know we could probably combine steps here, but just so we can see the rules in play, I'm going to do it this way. I'm going to give that negative 6 the free ride, and now the question is, what's the derivative of x to the fourth? That matches my x to the n perfectly again. So I've got 4x cubed here. When it comes time to take the derivative of the 1/2 x squared, that positive 1/2 is a constant factor. I will give that a free ride. And now I've got to take the derivative of x squared. Again, that's x to the n exactly. So the derivative of x squared is 2x. And then the last piece I've got here is the derivative of negative 6. But keeping in mind that negative 6 is a constant term, the derivative of all constant terms is going to be 0. So I'm pretty much done taking the derivative of this side of the equation. But what you have to understand is we do the same thing to both sides. So I've taken the derivative of the 4 terms on the right-hand side. I now have to take the derivative of the left-hand side. This one is not going to match our one steps perfectly because I'm trying to take the derivative of y. So I want to make sure you guys understand the operator. You saw this operator written on each of my one steps, okay? You see it written right here when I wrote the derivative of x to the n. What does it mean? Well, this operator is telling us that we are about to take the derivative of whatever we put inside those brackets. So I'm saying we're trying to take the derivative of the left-hand side and the right-hand side. Well, the right-hand side is done. We've got the four terms. That's great. Now we're taking the derivative of the left-hand side, which means I'm actually taking the derivative of this guy right here. I'm taking the derivative of that y, which means this is the way I would write the derivative of that left-hand side. But the beauty of this is a notational concept. The derivative of y is literally just called the derivative of y. This actually is the answer. So when I come over here and I write dy over dx, one of the things I want to make sure you understand is we're not writing that because we're supposed to. We're not writing it because it's what we named it. We're actually writing it because we took the derivative of the left-hand side. We took the derivative of y, and the correct notational way of writing that is dy over dx. You'll hear me refer to that as a notational one step throughout the course of the evening. If I take derivative of y, dy over dx is its notational one step, or y prime. If I take derivative f of x, f prime of x is going to be its notational one step. So now kind of going back and just cleaning up this answer a little bit. Dy over dx is what we call the derivative of the left-hand side. It's the derivative of y. And now I can go through and simplify. 5x to the fourth is nice. We don't have to do anything there. In this expression, we have some factors that can be multiplied together. That's going to be negative 24x cubed. Over here, we've got a 2 times a 1/2. That's going to cancel and give us a 1, so just a 1x there. And the 0 can be left off. So our final answer can be written as the derivative of y with respect to x, or dy over dx, is equal to 5x to the fourth minus 24x cubed plus x. So if everything I've done so far is sounding good to you, is making sense, if you can give me some kind of a positive comment, a thumbs up, or sounds good, that'd be great. I'm going to go on, and now I'm going to go and put on the next example. And what I'd like to do is get you guys thinking about, is this a one step? Now, we've already said you can go term by term. So the fact that we have multiple terms is not a problem. So really, when I say, is this a one step, we're asking, is each term a one step? So let's just talk about each one kind of quickly. The first one is f of x. And just like before with the y, that is a one step. That's a notational one step. As long as I have f of x and I'm taking the derivative, I can use notation to represent that. So I'm feeling pretty good about that being a one step. So now when I look at the next term, I'm looking at this 20 tangent x. Well, the 20 prevents it from looking exactly like a one step, but at the same time, it's a constant. So we should recognize this as a constant factor, and that's going to get a free ride. So really, the only question is tangent a one step? And you may remember all 6 trig expressions are one steps. So tangent is a one step. And then the last one is our secant x. Again, negative kind of throws it off, but that negative is going to get a free ride. So the derivative of secant x is one of our basic derivatives. This one, we can literally just go term by term and take the derivative. So when we take the derivative f of x, that is a notational one step. We're going to call that f prime of x. The next term, we're going to take that 20. We're going to give it a free ride. Now it's waiting for the derivative of its attached part. Well, that's tangent, and this is where you got to remember, one tangent to 2 secants. Okay, one tangent to 2 secants. So there's my tangent. I now need 2 factors of secant. This will give me an expression of secant squared for the derivative of tangent. And now when I do the next one, what I like to do is I like to take that negative and treat it as a -1 and give a -1 a free ride, which is the same as just putting negative with parentheses. And now I'm looking at taking the derivative of secant x. But again, that's our ratio, 1 tangent to 2 secants. I've already used 1 secant. Here's my second secant. Here's my tangent. So I now have this done going term by term. And again, we can rewrite this just a little bit, get rid of some of these parentheses. They're not necessary. So we got 20 secant squared x minus secant x tangent x. One thing you might want to think about for future problems, in a lot of the examples we do, we're not going to just take the derivative and finish with that. We're going to take that derivative and do more math with it. So even though I'm not going to focus on it this evening, you might want to start to think about, are there ways I could do factoring for these type of problems? Because, factoring is a very useful tool. Here we've got a common factor of secant. There might be some other things you see throughout the evening. That's kind of something you want to keep in mind as we learn what to do with our derivatives in the future. But for right now, our real goal this evening is just finding these derivatives and making sure we're good at differentiation. So that's our first trig example. We're going to go to the next one. And what I'd like to do here just for a moment is give you about 60 seconds to take a minute and see if you can start to think about this derivative on your own. So I'm going to give you about 60 seconds, and then I'm going to check in with you. I will remind you that the free ride rule is in effect, as is term by term. You're going to want to be thinking about both of those. So go ahead, I'll check back with you in about 60 seconds. All right, so when you're looking at this one, the key is trying to figure out, are these one steps? Because some of these terms really don't have that feel of a one step to them. But if we go through them and kind of look at them one by one, I think you're all going to agree, at least I hope you're all going to agree, that g of x is going to be a notational one step. We're not really worried about that. So we're going to be able to take the derivative of the left-hand side by using g prime. Then as we continue, let's start with this one. Nice, easy one, right? Constant term. And you know that the derivative of that constant term is going to be 0. So those two are going to be fairly straightforward. It's these other two that we really want to think about. So this 14 over x cubed, does it look exactly like a one step? I'm going to show you something right now, and this is the biggest mistake my students make. So please do not do this yourself, okay? But the biggest mistake my students make is they take that 14 over x cubed and they want to say, well, 14 gets a free ride, and they say x cubed is a one step, and that would be 3x squared. Do not make this mistake. Why is this wrong? Why is it that I can't just take this derivative like that's x cubed, okay? And the reason goes back to something I'm trying to stress. To be a one step, you've got to look exactly like a one step. We have no rule that says x to the n in a denominator. As long as that x to the n is in the denominator, we cannot take this problem using a one-step derivative. So now the key is there a way to get that x out of the denominator? So I know you guys have done a lot of work in algebra, pre-calculus in your past. Give me an idea over there in that chat. What am I going to have to make use of here to help me get that x out of the denominator? The reciprocal I hear negative exponents, okay? So our goal is to try to rewrite this 14 over x cubed as something with x to a power up here, okay? And the right answer that I'm looking for here is to take that x cubed and move it up to the top by using negative exponents. So if you remember that x to the negative 1 is the same as, anybody in the chat, x to the negative 1, what's that the same as? There we go, Bufu. Thank you. And Michael and Abby, you guys got it. That's the same as writing 1 over x to the first, okay? Likewise, x to the negative 2 would be the same as writing 1 over x squared. So what we've got is x to the negative a is the same as 1 over x to the a. So we're very used to taking a negative exponent and getting rid of it. Can we use it in the other direction? And if you can, these one-step derivatives are really, really going to help you out a lot. So what I'd like to do now is I'm not even going to take the derivative. All I'm looking at doing is rewriting this so it looks more like x to the n. So you're going to see me just copying down the parts I'm comfortable with. G of x is good to go. We don't have to mess with that. But that 14 over x cubed, what I want to do is say that's 14 times 1 over x cubed, and that 1 over x cubed can be rewritten as x to the negative 3. Moving along, the next thing I've got is 5, and now I've got a square root of x. So now, again, you got to remember your exponent rules here. The square root of x, that's the same as using what exponent? Can you give me an idea in the chat? The square root's the same as, and there you go, Christiana, fractional exponents, x to the 1/2. You guys got it. So this is going to be rewritten as x to the 1/2. And I always like to say power over root when I make this switch. So because the power on this x is 1 and the root is the 2, we can write this as x to the 1/2. And then the next term is just going to be a plus 3. One thing I want to make sure you notice, I haven't done any calculus. There's no calculus being done here. I haven't taken any derivatives. I am just rewriting this problem. And the idea is this example here, the 14 over x cubed, is not exactly looking like a one-step with a free ride. But when I write the 14 in the front, that's a constant factor, free ride for that. And x to the negative 3, that's going to give me the ability to use a one-step. And the same is true for the 5 root x. So once it's in this form, let's go. Derivative the left-hand side, notational, that's g prime of x. 14 will get a free ride. And now I want to use the x to the n rule. So that's going to be negative 3x to the negative 3 minus 1, which is going to be negative 4. I continue by giving that negative 5 a free ride on the next step. And now I'm looking at the derivative of x to the 1/2. Well, the rule works for any number, so it's going to be 1/2 x to the 1/2 minus 1, and that will be negative 1/2. And now I've got the last term, and the derivative of 3, that's a constant, so we're going to get 0. So my first initial answer is this g prime I've just written, but now I want to go back through and I want to think about how can I simplify this. Big part of taking derivatives is understanding your negative exponents. I change back and forth freely. In the beginning, I wanted the negative exponent so I could take the derivative. Now that I've got the answer, I don't want the negative exponent. I'd rather see it written without negative exponents. So every time you see a negative exponent, please think about a fraction. So I've got some factors here. I've got I've got 14. I've got negative 3. Both these factors do not have negative exponents. They're perfectly happy the way they are. I can multiply these two factors together, and negative 3 times 14. That's going to be negative 42. So I'm going to end up with negative 42. And because that has a positive exponent, it can stay in the numerator. But now I've got x to the negative 4th, which is in the numerator. So when I bring that to the denominator, it's going to be just x to the 4th. Moving along, I go to the next term. I see a negative exponent again right there. So right away, I'm thinking about a fraction on this one. I go ahead and I take on the two constant factors, and that's a negative 5 times 1/2. So that puts a 5 in the numerator, a 2 in the denominator. And now I've got to deal with the x. X is in the numerator now with a negative exponent, which means it's going to drop to the denominator with a positive exponent. So I can leave the answer just like this. G prime of x equals negative 42 over x to the 4th minus 5 over 2 x to the 1/2. Keep in mind that x to the 1/2 can be rewritten as a square root. So this is not necessary on the AP exam, but some of us might be more comfortable with this notation. Using it as a 1/2 power or a square root, both of them are acceptable. So again, the idea here for the problems we're looking at tonight is how do I make these guys look exactly like one-steps? Let's go and take a look at some others. Here's a good example, okay? And again, don't fall for the trap. Cosine by itself is a one-step. Cosine in the denominator does not match perfectly. So how are we going to tackle this one? The best way to tackle this one is to think about your trigonometry and be familiar with your trig. A cosine in the denominator, what's that the same as? Okay, so let me throw that out there to you. If you've got a cosine in the denominator, it's the same as having what? That's it. There you go. It's the same as having a secant. So the idea here, again, is to rewrite this function so it looks more like one-steps. So I've got a choice. I can try to take the derivative of this expression, which is not a one-step, or I can take the derivative of this expression, which is exactly a one-step with a free ride. I think you know the choice I'm going to make. I'm going with the 10 secant x. So the derivative of the left-hand side is h prime of x. On the right-hand side, 10 gets a free ride. And now the derivative of secant, Well, 2 secants to 1 tangent. So there's my second secant, and there's my tangent. So that's just going to be 10 secant x tangent x. Knowing your pre-calculus, your trigonometric manipulations, your algebra manipulations, extremely helpful when you're talking about these derivative problems. Let's take a look at the next one. I'd like to give you guys another 60 seconds or so to start thinking about how you would tackle this one. So go ahead, give it some thought, and I'll check with you guys in just a minute. All right, so when looking at this one, the left-hand side of this problem, not going to be a problem. We're taking the derivative of y. That's a notational one step, so we're going to be okay with that. I see a Bofu, and I hope I'm pronouncing your name correct. That he's bringing up something called the quotient rule. Now, the quotient rule is a valid rule, but tonight we're focusing on how do we use these one steps. So is there a way we can kind of shortcut even the quotient rule here? So again, I want to make these look as much like our one steps as possible. We really don't have division when we're talking about our one steps. So what the idea is here is we want to make sure one of the most basic algebra things that we know is just hidden in the problem. Most students don't see it. And the thing that I want you to think about is when I tell you guys to look at this expression right here, if I showed that to a fourth grader and I just said to them, what is this expression? What type of expression is this? What's it called? They might not recognize the x's and the powers, but they'll recognize the structure. They'll see that horizontal bar there, and they'll tell me that this is called a what? Type it in. Come on. A fraction. That's it. So everyone recognizes this is a fraction. So now the next piece of the puzzle is if you ask them, this guy right here, and I'm highlighting right here, and this one right here, I'm highlighting that guy right there. What kind of symbols are those? Well, they'll get that right too. Those are subtraction symbols. So what you need to do is you need to look at this. There you go, Amanda, subtraction, exactly. So when you look at this, you've got to think to yourself, I'm seeing subtraction and I'm seeing a fraction. My fourth grade teacher, Mrs. Thompson, drilled this into my head. Anytime you want to subtract fractions or add fractions, what do you need to find? Every single time, okay? So in order to add or subtract fractions, come on, help me out. What do you need to find when you're doing that thing? There we go. Everyone's got it. Common denominator, common denominator. So here is the hidden piece of this puzzle. We came late to the party. Someone has already added or subtracted these fractions. We got the end result here. They have found the common denominator for us. But how many fractions did this expression originally come from? So the idea is to look at this expression and say, how many fractions were there before they combined them? So when you look at this, this is the result of combining how many different fractions? That's it, Jack. You got it. 3. So what I want to do now is I want to set this up as one fraction minus another fraction minus a third fraction. And if we do that, we know we have to have a common denominator. But remember, we came in at the end of the problem. The common denominator is already found for us. It's x's. I'm sorry, it's an x everywhere we look. So our first numerator, x cubed. Our second numerator, 6x squared. And our last numerator is 2. If you train yourself to look at this, you can save a lot of time by changing these problems to much simpler forms. Because now we can go further and we can start reducing these fractions. X cubed over x, that's x squared. And the better thing is it's exactly a one step. We look at this next one, 6x squared over x. Again, reduce it. That's just 6x. That's a one step with a free ride. And I saw someone mention in the chat already that this last one reminds me of one of the problems we did earlier. We've got an x in the denominator, which doesn't look exactly like a one step, but we can make it a one step by taking that x and bringing it up to the numerator, but that requires our use of negative exponents again. So we can actually change this expression to 3 one-step derivatives. So as we go through and we start taking it from the left-hand side, the derivative of y is going to be dy over dx. The derivative of x squared, exactly a one-step, that's 2x. The derivative of negative 6x, well, that's negative 6 is a free ride, and the derivative of x to the first, and I'm going to do this out, it's the first time we've actually seen it, it would be 1x to the 0 when I subtract 1. Okay? But if you remember your 0 power, you know that x to the 0 is the same as 1, so we're going to have some more simplifying to do there in a moment. Then the last one, we're going to give a free ride to the negative 2, and we're going to use the x to the n rule to make this negative 1x to the negative 1 minus 1, which is going to end up being negative 2. So let's start cleaning this up a little bit. We're going to get 2x. We're going to get minus 6 because that guy is going to turn into a 1. And then over here, we're going to get negative negative, which is going to be plus 2. And this right here is really x to the negative 2. So that ends up becoming a denominator of x squared. So we've got dy over dx equals 2x minus 6 plus 2 over x squared. So this idea of simplifying by using this, I call it splitting the fraction, but it's really using common denominators, very, very, very useful. And I'm just going to give you a heads up. Eventually, you will, if you haven't already, you're going to learn something called a quotient rule. Now, when you learn that, you could try to apply the quotient rule to this directly. And you'll get the answer. You'll get the same answer we got tonight. But as you go and learn more calculus, there's going to be some topics down the road where you're not going to be allowed to use a quotient rule, and you're going to have to understand the algebra of this problem. So I really, really hope you'll take this idea of splitting the fraction to heart and try looking for it wherever you can. Next example we're going to look at. Again, I'm just going to give you a few moments to do this one out. So take a moment, and I'll check with you guys in about 60 seconds. Okay, I've got some suggestions over on the side. I like it. When you look at this problem, it is not a one step. It does not match perfectly to the one step. So you've got to think, what can I do to make this look more like one step? And I see people saying, multiply it out, FOIL. You guys are on the right track. You've got exactly the right idea. But one thing I do want to point out about this one is, who's the independent variable in this problem all of a sudden? Come on, you can answer it. We've switched our independent variable. Thank you. We've switched it to t. Now, does that matter? And the answer is no. There's no rule that says x has to be the symbol that we're always going to use. But please keep that in mind as we talk about the notation in this problem, because the independent variable is a t now. So just going along with what you guys already started to say, this isn't a one step. So we've got to make it look like a one step. That's going to require doing some foiling. I'm going to do this out. It's going to be 25t to the 6th. It's going to be minus 30 and another 30 minus 60t cubed. And that's going to be plus 36. So when we multiply this out, we go from having this squared expression to having 3 terms. Now, when we look at these 3 terms, can we take the derivative of each term individually, go term by term? The answer is yes. Do they all match up to one of our one steps? Again, the answer is yes. So we are just going to go right down the line and take the derivative of these individually. This time, pay close attention to the derivative of the left-hand side. When I take the derivative of y here, you could write y prime, but I'm going to ask you guys for a little bit of help on this. If I'm not going to use that notation, I'm going to use the other notation I've been consistently using tonight. How should I call the derivative of y this time? What's it going to be? And there we go. Okay, good. You guys are paying close attention to our independent variable. So this is going to have to be dy over dt. And now we're going to go term by term over here. Free ride rules in effect. So we're going to do a 25 free ride. The derivative t to the 6th, 6t to the 5th. Negative 60 is going to get that free ride. We're going to do 3t squared. And then we get to the derivative of 36. That's a constant term. The derivative of constant term is always going to be 0. So notice, even though I'm using the x to the n rule, it still applies to t, because x really is just our short notation for the independent variable. So no one wants to say the independent variable to the n, so we shortcut it to x. Just keep in mind, it doesn't have to be x. T is perfectly acceptable as long as that's the independent variable. So now we've got dy over dt, and if we multiply this out, we're going to get 150 t to the fifth minus 180 t squared. And that's going to be our answer for this one. We got a few more examples to look at this evening. So why don't you go ahead and take a moment and look at this one. I'll check back with you in about 60 seconds. I hope you've taken a look at this and you realize right away that these cosecant squareds, cotangent squared, these don't look anything like a one-step. There is no rule for two cosecants multiplied together in our one-step list, okay? It's got to be just cosecant by itself. So can we take this derivative with the rules that we've discussed this evening, okay? Now, there may be some future rules coming up where you might have rules that you can do, but again, everything we do tonight goes back to being a one-step, going term by term, having the derivative of a constant term or the derivative of the constant factor. So the one thing I do notice on this one right away is we've got sixes in both cases. So how about we may take advantage of that constant factor? How about we take that 6 out? And now we've got cosecant squared x minus cotangent squared x. Well, I mean, it makes it a little bit better, I guess. We've got a constant factor, but we still have these cosecant squareds and cotangent squareds. So any suggestions on what we might have to do here to try to get this into a form of a one-step? This is where your pre-calculus knowledge is going to have to come up big, okay? In my pre-calculus class, we always talk about using trig identities to make our lives easier. And the number one trig identity that students remember in my class is sine squared x plus cosine squared x equals 1. Now, you might not think that has anything to do with this example, but you also need to remember that every trig function can be built from sines and cosines. So I want to kind of focus on the cotangent squared for a second, because cotangent squared can be thought of using sines and cosines, because cotangent is really the same as cosine over sine. So if I want a cotangent squared, that would be the same as me writing a cosine squared over a sine squared. But here comes the I can do anything I want to an equation as long as I do it to both sides correctly. How about I divide everything on both sides by sine squared? And if I do that, what I really have now is 1 plus cotangent squared equals, and 1 over sine squared is cosecant squared. Well, all of a sudden, this is now starting to match up a lot better to my problem. I've got a cosecant squared minus cotangent squared. On this side, I've got a cosecant squared. On this side, I've got a cotangent squared. So how about I subtract cotangent squared from both sides? If I do that, I will find out that 1 equals cosecant squared minus cotangent squared. And that little piece of information is going to be huge in this problem, because I can now go and replace it here and rewrite my problem as f of x is really equal to 6 times 1. And therefore, f of x is a constant, which means f prime of x is just going to have the answer of 0. So trig identities, big part of simplifying your life when you're talking about taking derivatives. Here's another example for you guys, kind of along the same lines. And Again, first thing I noticed is I have made a little bit of a typo on this one. I wasn't trying to trick you. Let me rewrite this one. A little bit of a typo. This is really 12 theta cosine theta secant theta. So I mistakenly put an x there. That should really be a theta. So theta squared. Okay. So now when you're looking at this one, okay, when you're looking at this one, trigonometry again plays a huge role because every trig function can be thought of as sines and cosines. So if you think about secant, what's the other way to write secant? Well, a secant is the same as having a 1 over cosine. So rewriting it gets those guys to cancel, and this becomes r equals 12 theta squared. Now it's just a one-step derivative of the free ride. So the derivative of r in this case, this would be dr over d theta. And now the derivative of 12 theta squared will be 12 times the theta squared derivative will be 2 theta. And that will give us a final answer of 24 theta. Okay, so we're looking at ways we can simplify. We're kind of practicing some of our algebra and our pre-calculus skills. Here's an example that I actually put on a very similar one on my students' homework this other day. So if any of my guys are still watching, you're about to get one for free tonight. We're looking at the derivative of cosecant pi plus 1. And every year I get students come back and say, how do I do this one? I've got a derivative of cosecant, but what does the pi plus 1 do? Well, you got to think about this one a little bit. First of all, 1 by itself. Anybody still out there? Is 1 a variable? The answer is no. 1 is considered to be a constant. What about pi? Is pi a variable? Again, the answer is no. Pi is a constant. So if you take one constant and add it to another constant, the result you get is a new constant. So now what we're asking is, what is the derivative of the cosecant of a constant? But anytime you take a function and plug a constant in, you get a constant out. What I'm trying to tell you is, there is no variable in this problem. Cosecant of pi plus 1 does not have a variable. If it doesn't have a variable, it is just a constant. And if it's just a constant, no matter how it looks, the derivative of any constant is always going to be 0. So this one's just kind of a common sense problem. The derivative of f of x is f prime of x, and the derivative of this constant, which you might not be comfortable looking at first, but it's still a constant, ends up being 0. The biggest clue here is the independent variable is x, and when you go look on this other side, there are no x's. If you don't have a variable, you are a constant. So the derivative of this constant has to be 0. We've got one more example to look at this evening, and as we're wrapping up, if you have any questions at all, if you want to put them over in the chat, please put them over in the chat. I can stick around a few extra minutes to answer any questions that come up. But I'd like to give you just a moment to take a look at this example. So again, another 60 seconds on this one, and then we'll wrap up for this evening. All right, as we look at this one, the first thing that I notice right away is we've got a fraction. And again, the one steps do not have variables on the top and the bottom. So the question is there a way to simplify this fraction? And to me, the key is noticing that degree 2 up on the top. Anytime I see degree 2 up on the top, I've got to think about factoring. And the bottom, pretty clear, greatest common factor of 2. So we'll take that out and make it 2 times x minus 1. And I see some people over in the chat talking about factoring and canceling. That's exactly where we're going. So as we look at this guy, we're going to find a factor. Let's see, we're going to need a 3x and an x, and then we're going to need factors of -5 that are going to kind of work together in this one. So what I'm hoping is that we're going to get a -1 here and a +5. Let me just check that real quick. 3x squared, negative 3x, positive 5x. That's going to give me my 2x, and negative 5 at the end. So this is going to work. And when we see this, we now see common factors of x minus 1. So all of a sudden, f of x is equal to 3x plus 5 over 2. But this gives us a chance to talk about what we're the algebraic step we saw earlier. Terms in a numerator. You see terms in a numerator, we can do our thing called split the fraction. So we can write this with common denominators, and it's going to be 3 halves x in the first one, 5 halves in the second. The derivative of f of x is a one-step of the notational kind, so it's going to be f prime. The derivative of the 3 halves x, well, 3 halves gets a free ride. And now the derivative of x is going to be 1, because again, that's x to the first, so the derivative would be 1x to the 0. And then the derivative of 5 halves by itself, it's a constant term, that's going to be 0. So our final answer here is f prime of x equals 3 halves. I'd like to thank everyone for joining me tonight. Like I said, I'd be happy to stick around for a few minutes. If you enjoyed this evening's presentation, if you could give me some kind of feedback over on the chat, I'd really appreciate it. But aside from that, I'm pretty much going to wrap up for this evening. Tomorrow night, we're going to do another stream. That stream is geared more towards teachers, but any students who have seen implicit derivatives or derivatives of inverses, feel free to join us. That's tomorrow night at 8 o'clock, and then we'll be posting more streams for calculus later on this week. If you've got any topics that you're interested in seeing, please put them in the chat right now. We are more than willing to try to accommodate the topics that you guys want to see. So for all of you who joined me tonight, thanks so much. If you're one of my students, thanks for coming. Now go to bed and get some rest because we got big calculus to do tomorrow. Everybody else have a great evening, and thanks for joining us. Bofu, you're asking for integrals. I promise you integrals are coming. Mean value theorem, we will be definitely having a stream on that as well. And Rolle's theorem, of course, is just a subset of it. So yeah, we'll be doing those too.